So, welcome back. I wanted to start out with a hint on homework one, number 2, because that's the only one that really requires previous knowledge of stuff and expectations. So let me share my screen. Okay, so for problem 2 on homework 1, there's this balls and boxes things, and I gave you a hint about indicators. And if you don't use them, I'm sure you can do it another way, but it's going to be really hard, I think. So there are 5 boxes, 1, 2, 3, 4, 5, and then there are 7 balls being randomly put into these boxes. And so we want the expected number of empty boxes. And you were given a hint to use these indicators. So I gave you these indicators, this I for indicators, sub I, to be 1 if the I box is empty and 0 otherwise. And you could set it up the other way, but I kind of wanted to indicate when the box is empty, which is what I'm really looking for. And so the number of empty boxes is going to be the sum as I goes from 1 to 5 of I sub I. And so if you're taking the expected value here, you can pull that sum out. And it's weird, but you can treat the boxes independently. Expectation is a nice linear operator. So you can pull this out. And then if you haven't seen expectation of an indicator before, that's really what I wanted to talk about for a moment. An indicator is a very simple and discrete random variable. It takes on the value 1 or 0, and it takes on the value 1 whenever the box is empty. So just to look at one expectation alone, the expected value of I sub I is going to be 0 times the probability that I sub I equals 0 plus 1 times the probability that I sub I equals 1, which is just that last probability. Everything else goes away. And then I sub I is 1 if and only if the ith box is empty. So this is the probability the ith box is empty. And I know it seems weird, but you can consider this box alone because that's all I care about right now, the probability that the ith box is empty. And I don't care about it being box number 1, or I don't care about the other boxes because of this nice kind of linear operatorness of expectation. So to compute the probability that the ith box is empty, I don't want to completely finish this for you, but you've got these 7 balls and you are randomly putting them into boxes. And what is the probability that any one ball will make it into the particular ith box? It's 1/5 because you're randomly distributing them. So this is kind of a binomial sort of thing. You've got 7 things and you've got to get 0 of them into the ith box. So if you label falling into the ith box a success, the success probability is 1/5. And if you label the probability, and the probability of failure, meaning you do not fall in box 1, that probability is 2/5, and you got 7 tries. So it's a binomial thing to get one of those expectations, and then ultimately you put it back into the big sum. Otherwise, you could consider where everything falls, some kind of multinomial thing where you've got some things over here and some things over there, and that's really hard. Why are the indicators independent? That is a great question. And the answer is they're not. However, expectation is always a linear operator. So, we've got an I1 and I2 and I3 and I4 and an I5. And, if these 3 are equal to 1, that means all those boxes are not empty, and that makes it more likely for one of these to be empty. So they're definitely dependent, but the expected value of a sum, independent or not, is the sum of expectations, which brings you back around to just looking at one at a time. So you could have like a person sitting in every box waiting for the balls to come in, but just the ith person is like, hello, failure, 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 success, like they're counting for their own box. Okay, so we had the Rufus, that was my dog, mood chain, and he was one of three states each day: happy, just okay, or sad. And we had a probability transition matrix for happy, okay, and sad that looked like zero point 0.6, zero point 0.3, zero point 0.1, zero point 0.2, zero point 0.5, zero point 0.3, zero point 0.2, zero point 0.3, zero point 0.5. So happy, okay, sad. And we wanted to find, and we did, so this was question one, and I'm not going to, don't worry, I'm not going to drag you through it again, but I just did want to recap it. So question one, and one of the biggest parts of this is turning it from English into the math, but I won't work on this one again. We'll do that for the others. We had that Rufus was happy, and we want the probability that he's not sad on any of the three following days. So we wanted the probability that X1 is not sad, and X2 is not sad, and X3 is not sad, given that at time 0, he was happy. And so to answer this, I made another matrix that I called the Q matrix. Now, if you say Q matrix to someone else, they're not going to know what you're talking about. That's not a standard notation, but I think it will really be leading when you're doing these problems. If I say it's a Q matrix problem, you'll know exactly where to look in your notes. So we made a matrix. We made a copy of this matrix, but we made sadness an absorbing state, and we called the new matrix Q. And last time I didn't actually define a new Markov chain. I was trying to leave that kind of detail out, but let me do that here. So if the Markov chain running according to P is a chain Xn, and the Markov chain running according to Q is a new chain Yn, then we saw some example situations, like if we had the Xn chain starting happy and then being happy and okay and happy and sad and okay and happy and happy. But the Yn chain starting in the same place will follow those probabilities. So, oh, my screen sharing is paused. So as I write out the Ys, I'm trying to share my screen. The chain is going to look the same: happy, happy, okay, happy, sad. But once it hits sadness, it will be forever stuck in sadness. And so let me just, for cutting and pasting, jump back up here. The probability that we're trying to find, the probability of not being sad on any of those 3 days, that event is the complement of the event. So we get 1 minus the probability at least one of X1, X2, or X3 is sad, given we started happy. And so look back at the kind of sample paths I drew. Here, we are starting happy, and then we're happy, okay, happy. There's no sadness. And we can tell that by looking at the Y chain, because there's also no sadness. But if, say, time 0 started here, and we started happy, and we were sad, okay, happy, so that's our 0, 1, 2, 3 steps, we will determine that we saw sadness if the Y chain ends in sadness, because the Y chain will hit sadness at the same time as the X chain, and then it will be stuck there. So this is why I said this is 1 minus the probability that Y3 is sad, given Y0 is happy. And so the Y runs with the Q matrix. This is 1 minus the Q matrix cubed. I'm just making up this bracket notation to try to say cube the matrix first and then take the happy to sad entry. So that's old stuff. So just one more time. The Y chain ends sad if and only if. It ends sad if and only if the X chain was sad at least once. And if the X chain is sad at least once, then the Y chain will end sad. So the at least one of the X's being sad is equivalent to Y3 being sad. Okay, so at the end, I just stated question 2 and asked you guys to think about it. And now we can see if we got the same thing. So this is a really different question, though. So Rufus is happy on Monday. And I want the probability he's happy on Friday, given that he was not sad all week. And just to be clear, that does not include saying anything about Friday, which is actually my question 3. So let me write that and try to clear that up again. So what is the probability he is happy on Friday, given he was not sad all week? And so this not sad all week, I'm not including Friday. I don't know anything about Friday. It's another problem to be given that he's not sad on Friday, and then to compute the probability he's happy there. So this is not including or referring to Friday. It's not saying anything about Friday. Mhm. Okay, anything about Friday. So what we want is if you look at the days and you maybe label them with numbers. So here's a Monday, Tuesday, Wednesday, Thursday, Friday, and then you label these time steps 0, 1, 2, 3, 4. What we want is the probability that H4 equals happy, given that we started happy at time 0 and we were not sad for I equals 1, 2, and 3. Okay, so we would kind of like to have, I don't know, this guy, this xi not being sad over here. So we can do this kind of like our Q matrix problem. So I've got the probability that some event A happens given some B and C. And so this is the full intersection over the probability B intersects C. And then on the top, I can write this as the probability of A intersect B given C. Let me move this, times the probability of C over the probability of B given C times the probability of C. And then this will cancel. So you see what I did? I had two things on the given, by the way, means they're both happening, like an intersection. So I have two things on the right side of the line, and I can move one over, and I will get these extra C probabilities, but they're going to cancel. So my point is, I'm not saying this very well, going back to the problem, this is going to equal the probability that X4 is happy and Xi is not sad for I equals 1, 2, 3, given X0 is happy, over the probability that Xi is not sad for I equals 1, 2, 3, given X0 is happy. So I made this event be like my event A, and this event is like my event C, and then this event is like the B. And so now the denominator is just what we computed before. And the numerator is, well, let's simplify the numerator. So in the numerator, we're going from happy to happy, never having passed through sad. So that's the probability of going from happy to happy in 4 time steps, never having passed through sad, which is the same thing as going from our Q matrix in 4 steps, going from happy to happy, because the Q matrix is ruling out that we went through sad, because if we went through sad, we cannot make it back to happy. And then the denominator is what we had before. Okay. You know what? When I finished, oh, I did. Okay. I didn't know if I put the 1 minus there. So this is 1 minus the Q matrix cubed, happy to sad. Thought maybe this was worth doing because at first I was going to start trying to rewrite. Actually, let me go back further. No, that's where I want to be. At first, I was going to start to try to rewrite this and move things back and condition on things. but maybe it's just easier to go down to like 3 events representing 3 different parts of this. Yes, you're absolutely right, but we didn't observe Thursday. So we want to know the probability we're happy here, given we were happy here. And we never got to observe this, like something went on in between. So if this is Monday, Tuesday, Wednesday, Thursday, Friday, well, yeah, let me not make it so complicated. The day before, right? Day before. All we know is it's not sad, and we actually don't know what it is. It has to be fixed for us to be able to use that Markov property. If we want to try to, these are not fractions, by the way, these are my slots with a Thursday and Friday under them. If we knew that on Thursday we were okay, then we can find the probability of going from okay to happy. We can just read it out of the P matrix. And if we knew on Thursday we were happy, we can read the happy, happy entry out of the P matrix, but we don't know which one it is. So to do this, you would have to maybe condition on which one it is. You would have to say, what is the probability that, I'm going to change my whole notation up, that X Friday, because I don't have time points here, is happy given X Thursday is happy times the probability that X Thursday is happy, or the other event, the probability that X Friday is happy, F, given X Thursday is okay times the probability that X Thursday is okay. And now maybe you see the problem. These first 2 conditional probabilities can just be read off the P matrix, but we don't know what these are. So we'd have to condition and go back further and further. And this problem, we didn't even have an initial distribution. So eventually we're going to get to a point where we can't find the probability we need. The Markov property says given that a value is known, not given that some values are ruled out. Okay, so I have 2 more questions for Rufus on my third one. On my third one, we have that Rufus is happy on Monday. And I want something very similar to the last one. The probability he is happy on Friday, given that he was not sad all week, including Friday. Given not sad all week, including Friday. Okay, so the only difference between this and the last one, in fact, I'm going to go back to the last one and cut and paste and then change it. So the question in the last one, okay, so this is not exactly what we want. What we want is now, we know he's not sad also on Friday. That's what's changed. This is kind of what we were just saying though about, okay, now we know some information about Friday. We know he's not sad. So the probability, remember, time step 4 is Friday. We know he's not sad on Friday. So the probability of him being happy is going to be larger than it was before because we've ruled out sadness. So a kind of question I like to ask on exams is I like to pose both of these problems, this type of problem, and say, which probability would you expect to be larger? And again, if this was not here and we just want the probability of being happy on Friday, that's one thing. But if we are given that we are not sad on Friday, then we only have 2 possibilities for Friday, happy or okay. So we've increased those probabilities. So we expect this to be larger than what we got in question 2, although I didn't take it to its numerical conclusion. Right, so I'm going to do the same thing, and I'm going to skip kind of the steps where I wrote in the corner, okay, A given B intersects C. I'm just going to go to the same sort of conclusion, which is I can move everything to the left side and leave the X naught equals H on the right side. And I will get, so X4 is H, and Xi is not sad for I equals 1, 2, 3, and 4, given X naught is happy. And really, although you don't have to write this, this should be times the probability that X naught is happy, because that's going to cancel with what's in the denominator. X naught is happy. So that's going to go away anyway. Okay, the bottom is just 4 steps where we start happy and we have not hit sad by time 4. So the denominator here is going to be 1 minus q to the 4th. That's not a q, that's a theta. My absorbing matrix q to the 4th, and I want the probability of going from happy to sad, and then 1 minus that is the complement. So that's everything else, meaning I never hit sad. And then the only thing that's really changing, I guess that changed actually, is on the top, I know or I want the probability that X4 is happy and also X4 is not sad. But that is redundant information that X4 is not sad. The probability that X4 is happy and also not sad is the probability that X4 is happy. You get to drop the 4th one because it's redundant given this piece, not given. And so the numerator now is going from happy to happy in 4 steps without ever going through sad. So this is going to be the HH, the happy to happy entry of Q to the 4th. I have one more with Rufus, and it's going to be really, really short because it's just to make a Markov point. So question 4, he's happy on Monday, and I want the probability he's happy on Friday, given he was not sad for the previous 2 weeks. And it's hard to write this for me, at least in English. So I'm assuming no information is given about Friday. Okay, so we've already done this because we've got we have our Monday, Tuesday, Wednesday, Thursday, Friday, Tuesday, Wednesday, Thursday, Friday. We're happy here. We want the probability we're happy here given we're not sad for the last 2 weeks. So this can go much further back, but by the Markov property, the last given value is all that matters. So this is exactly what we computed in question 2. I don't really want to write out the notation for this. I don't want to put in like 15 days of subscripts. So this just doesn't matter is the point by the Markov property. So this is the same as question 2, where we started happy and we wanted the probability we were happier on Friday, given that we were not sad for the 3 days in between. Yeah, again, all I care about is he's happy here, don't know, oh, not sad, not sad, not sad, and then happy. All right, next up, this deserves its own new slide. I want to talk just briefly about a longer history in a Markov framework. The way we're going to do this now is going to be pretty clumsy, but it's a first attempt at putting more days into the Markov framework. Okay, so I have an assembly line, and I'm going to be really lazy. Of course, this is always what I think is the important part, write out the English so that we know how to transform it into the math. But I have an assembly line producing items that are either good or defective. And so I have some rules here. If I'm going to write out 1 in its entirety and then do some ... kind of stuff. So if the last 2 items were defective, let's say that the next is defective with probability 0.4. So I need a couple of days of history here. And then this is going to be the same, but I'm starting with the last 2 items being good, and then the next is good with probability 0.95. And then don't worry, I only have 4 bullets here. So if the last is defective and the one before that is good, then I'm going to say that the next one is defective with probability 0.2. Okay, and then my final one is going to be You'll get this when I type it up, but I'm sorry it's so sloppy. The next one is going to be if the last one is, so I'm copying the line in front of me, just above me. The last one is good, and the one before that is, I need to write this out. I'm sorry, I'm going to make a mess out of this. So one more line. If the last one was good and the one before defective, the probability that the next one is good, I'm going to say is 0.85. So although 2 days of history are mattering here, we could think of the 2 days, the next one is defective with probability 0.2. Okay, so let's look at the kind of, I don't know what you want to call this. I'm running into the same sort of language issue with my Monday, Tuesday, Wednesday, Thursday. So maybe this is the last one. What I mean is this is now, and then this, and then the first column is the previous one. So I could have good, then good, I could have good, then defective. I can have defective, then good, and defective and defective. And I don't need to do this, but it's helpful when the problems get bigger. I can label these states. I'm going to call this 0, 1, 2, 3. By all means, call it 1, 2, 3, 4. I'm just Markov indoctrinated. So let's find a probability transition matrix. 0, 1, 2, 3, 0, 1, 2, 3. And so there's a little bit of overlap between the days. If you want to go from 0 to 0, that means you want to go from good, good to good, good. But what that really means is that you have 3 goods in a row. Good, good, good. And you're going from this state to this state. So this is not exactly accurate here, but this is. And so I think the first line I gave, the second line I gave, if the last 2 were good, the next is good with probability 0.95. So it's going to go up here in the matrix. Okay, so if the last 2 were good, then the next one is either good, which we've already covered, or defective. So we can go from good, good to good defective. So this is like state 0 to state 1. And that is all the possibilities there are, because we can't go like from good, good to defective, defective in one step, because the middle ones have to overlap. So I can go from 0 to 1 though, and that's the remaining probability across the top row of this matrix. Okay, let me do one more and then I'll just fill it out for you in the interest of time. So starting at state 1, so I'm trying to go for this one row of the matrix. State 1 is good and then defective. And so starting there, starting from 1, I can go from good defective to good, and I can go from good defective to defective. So good defective is state 1, and then defective good was state 2. Over here, good and defective is state 1, and defective defective is state 3. And looking back at all of those lines, that if the last, yeah, I'm in my third bullet. If the last is defective and the one before that is good, the next will be defective with probability 0.2. So that is this one. And then this gets the rest of the probability. So I'm going to copy the matrix. So the one row of this matrix is going to look like 0, 0, 0.8, 0.2. You just have to have overlap in between them. And then continuing this, I get 0.85, 0.15, 0, 0, and I get 0, 0, 0.6, 0.4. And now we can ask a bunch of questions. I'm not going to ask too many, but note that some things that you might think are 2-step transitions are really not 2-step transitions. So question 1, given that the last 2 were defective, what is the probability that the next one is good? This is something you can just read off the matrix, right? Because we're going from defective, defective into defective, good. So that is 3 to 2. And you can just grab it off the matrix. The answer is 0.6. Not interesting. So let me do another one that is probably also not interesting. Question 2. So I'm given that the last 2 are not defective. What is the probability the next 2 are good? This is such a horrible way to write down this question. I am rushing, but really what I want is a conditional probability. So I guess I should have, why did I have to rush for that? Given that, I'm going to just state it right now because I'm almost out of time. Given that the last 2 are defective, what is the probability that the next 2 are good? So probability next 2 good given the last 2 were defective. Okay, so now I want to go from defective, defective to good, good. And so I want to go from the defective to defective state, which is our state 3, to defective to good, which is our state 2, to good, good, which is our state 0. And this is not a 2-step transition probability. So a 2-step transition, this is the point I want to make by doing this other example. If I wanted a 2-step transition, that would be like me going from 3 to 0 in 2 steps and not worrying about what happened in between. So technically, this should not come out of a p-squared matrix. Although, in this case, there's only one way to get from 3 to 0 in 2 steps. You must go through 2. So using the p-squared matrix would actually work here if you looked at the 3 to 0 entry of p-squared, but it's only kind of a fluke of this problem because there's only one way to get from 3 to 0 in 2 steps. And just go from 3 to 2 with probability 0.6, and then from 2 to 0 with probability 0.85, which is 0.51. But the real point I wanted to make one more time is that don't try to do a 2-step thing because we are not, 2-step is for skipping things. You know, what is the probability Rufus is happy on Tuesday given he was happy on Sunday? Like, you're skipping a day. You're not talking about all 3 days. I am almost out of time and I owe you time anyway. I think you're going to be happy with our next class because we're going to start really getting into, we're going to get out of these probability kinds of word problems and stuff. And next time we're going to talk about classification of states of a Markov chain. So some states in the state space, once you hit them, you could be absorbed and stuck there. Some of them, once you leave them, you could never return. Some of them, once you leave them, you'll return in a finite amount of time. Some of them, you'll return in a finite amount of time with probability 1, but the expected number of time steps is infinite. And we have all of these things to, all of these ways to classify states. And the reason we want to do this is because we have a bunch of theorems coming up about the limiting distribution of a Markov chain. So start your chain in some state, run it forever, collect the output at time infinity, do it again, collect it again, do it again, create a histogram at the end. We want to know that limiting distribution. And I'm going to have a lot of theorems that say, if this happens, if this state, if you can return to this state in finite time, then this will happen or that will happen. And I think this part was really fun. So please come back.
Oh no. Hey, where am I? Why are we out here? I don't think I... Stop poking me. I want some leaves. I love squash. Back in the bin. Do you like squash? No, I like squash. Move over. I want some. Yeah. Can I have a potato with that? No, I don't know. What? I hear a cow.
Yeah, bitch, I'm a cow. Bitch, I'm a cow. I'm not a cat. I don't say meow. Bitch, I'm a cow. Bitch, I'm a cow. Bitch, I'm a cow. Bitch, I'm a cow. I go moo. Moo. Too smooth.
This is oh no. Oh no. Oh no. Oh no. My eyes. Someone put the light on. I need you to. I also. So you like squash? I wish you could. Everyone. We're just trying to sleep under here. I don't think she sees us. Oh, I've got a good leave. Nobody move. Everybody. Did you see that fish pellet? Freeze. She's gonna freeze. We're gonna. I don't want to go out there. Stay still. Come on. She doesn't. No,
It's a very special friend of mine. my very favorite little pal. Oh, rubber ducky, you're the one. You make bath time lots of fun. Rubber ducky, I'm awfully fond of you. Bo-vo-bo-dee-o, rubber ducky, joy of joys. When I squeeze you.
Hey, who ordered the fish? Oh my god, fish! I love fish. Are you gonna really like fish? Fish are straight by the We're almost like vegetarian. We're crustaceans, you know, and yeah, it's time to lose that exoskeleton. Fish. I would never try that on. Otherwise, we're eating leaves. Fish. I can't get up. No. Oh, turn over. Hey. Oh, no. I'm getting it. Wait. Okay. So, oh. I'm a duck. I better make a break for it.